Hi, everyone, and welcome to our monthly virtual lecture. I'm Carla Gonzalez, and I'd like to introduce you to our speaker today, Thomas Campagne, who will be demonstrating the new data scripting functionality in Geoscience Analyst Pro. If you have any questions during the presentation, feel free to type them into the Q&A or raise your hand. It's likely that Thomas may wait till the end to answer the questions. And just a reminder that this lecture is being recorded and it's going to be available in our YouTube channel in the coming days. All right, and without further ado, Thomas, you're up.
Thanks, Carla. Thanks everyone for joining us today for this virtual lecture. I will demonstrate scripting, a new implementation of scripting in Geoscience Analyst Pro over a series of like three short examples. The first one will be focusing on geochemistry and will be applying scripts to drill assays. Then we'll move on to simple processing of radiometric data. And then we'll finish with a last example, which is a soft constrained inversion of gravity data. So we'll be working on the inflown area here, and it is in this Geoscience Analyst workspace here. I already have like a block model and drilling. So to start with the geochemistry, I will actually use my drill hole assays here. And the first step in this lecture would be to extract the points from my drill hole database. So to desurvey my drill holes. So I'll go under drill holes, desurvey drill holes. All the ones my entire database is already displayed, so they're already all selected. For the master log, I will select copper. The location would be in the middle of the interval. And then I will name my newly created desurveyed point set, desurvey, and click on apply. So this creates these points here that I will just organize and put in my geochemistry folder. I'll hide the drill holes. So now on all these points here, you can see in the object tree here that I've got a series of all my assay properties are located here. And we'll be using scripting to combine these geochemistry assays to compute two alteration indexes, so the Ishikawa index and the chloride carbonate pyrite index. So to apply scripting, you can right-click on any of these properties, and in the drop-down menu, I will select Script, which will bring up the scripting window here. So I'll just go through the window quickly. So you can select your objects here. You can apply scripts on all the objects in Geoscience Analyst. Association or nodes, you can select a masking property, the output name of the property that will be created through scripting. You can choose if that script has been run once already, you can choose to overwrite an existing property with the same name. The scripting field, where we'll put our scripting formula. A help button that I highly recommend for new users, as there is a wealth of information here with predefined constants, all the operators, examples as well, and tips on how to implement scripts. And the output field here is dynamically updated depending on what you type in the window here. And I'll get to that shortly. So first of all, let's get going and compute our Ishikawa index, which I will name AI for alteration index. Here we go. And the script itself is going to be, so I'll type this one by hand. And you can see that the scripting field down below is being updated as I type. And you can see here, if I start to actually type an existing property name, you can see that that property name appears in bold. So that's already a way to assess typos when you actually type a script. And then I will just complete the whole script here a bit faster. So here's the formula for the Ishikawa index. You can see that if I had made a typo for the calcium here, and I try to apply my script, I would get an error and the script will not run. So if I have the correct property name here and I apply, I then create a new property here that appeared on my object called AI. And here is the Ishikawa index on my entire desurveyed cloud of points. Now I can also compute the CCPI index. And here, I'll just grab the formula here. It's slightly more complex formula. And I will apply that as well to my object. So now, by applying simple formulas to the existing properties, I calculated two indexes here. And I can actually leverage that information one step further by actually creating a categorical properties based on criteria. And to do that, I will actually look at alteration trends and try to actually identify the chloride pyrite zone, which is typically associated with mineralization and has here we can consider Ishikawa index values greater than 80 and CCPI values greater than 90. So for my chloride pyrite zone, I'll just actually name it like this. And I will update the script with a statement here. So in that statement, I want values greater than 80 for AI and greater than 90 for CCPI. When this is true, all these values will be attributed with the chloride pyrite zone class. All the values that don't fit that criteria will be attributed with the others class. So I click on apply. And now I can see I have a new discrete property here on the object. I click on it, so it's now shown on the screen, and I can choose to hide others. And these points here are all the points that are falling within the chloride pyrite zone. So I can leverage that even further by nesting these statements into one another to create several classes in only one step. So what I'll do is that I want to create actually a classification of alteration. So I'll name that a new property called alteration. And the script will start the same way, but will actually include more criteria. There we go. So here, the beginning is the same, but instead of having an others class here, I replaced that by another statement here, where I want values of AI between 20 and 65, and value of CCPI between 80 and 15. And these values will be classified as least altered. And then all the values that do not fit any of the two criteria that are preceding will be put into intermediate alteration. I'm going to apply this. And now I've got an alteration property here on the entire point, which shows me the intermediate alteration, least altered, and the chloride pyrite zone as well. I can further refine this to only look at the points falling within a very specific lithology. So now on my drilling, I just displayed a flin-flon geology property here, and I will just show the mill rock member here. And I'm doing this to create a masking property on this object. So I'll right-click on the object now. I will create masking property. And here I will create through a visible association method. And the output name here will be mill rock only. That would be the mask. Okay. So now I've created that mask, and I can select it in my script as well. So here I will select masking, mill rock only, and alteration within mill rock. And I run my script again. So I'll just go back here. I will show everything. And now I'll get to show you the initial alteration classification that was done on the entire data set, and then the alteration within the mill rock only. And we can see that we've only extracted here the points falling within that lithological domains. So that ends up the geochemistry portion of this lecture. And now I will move towards the radiometrics. And here in the Flin-Flon area, we've got the publicly available radiometric surveys. And quite often when radiometric data are being processed and corrections are applied to the raw data, the corrections might overshoot a little bit and create negative values, especially here in that low. If we actually click on it, we can see that for the potassium here, we've got values in the negatives. Like if we look above the histogram of this property, we can see we've got a minimum of minus 0.036. So here's something we might want to do is to actually normalize the potassium values between 0 and 1. So we only have like positive values. To do so, I can right-click on the property, apply a script. It brings this window again. Don't want to do any masking here. And I will use the same base name for the potassium here, and I will call it Normalize. And the script here will actually make use of the values minimum and maximum shown above in the histogram here. And I'll use these values to actually normalize my data. So I will take my potassium property. I'll remove the minimum and I'll divide it by the total range of potassium data. I'll click on apply. And now I have a new property that has been created on my object. And if I look at it, so the color scale has changed a little bit. But if we look at the histogram, the distribution remained the same. And now we've got the minimum and at 0 and the maximum in between 1. So that was quite straightforward normalization here. And then now we're going to move on to the geophysics with the soft constraining version. So in this workspace, we have a geological block model here for the Flin-Flon area. So when I select the Flin-Flon geology property here, I can see I've got the color table here to the right. And what we're going to do is to actually compute the response of this model initialized with bulk densities, so homogeneous densities for each of these lithologies. We'll compute the response of this the gravity response of this model and compare it to the measured airborne gravity data that we have here. And when comparing it, we'll look at the residual data. So it will be the difference between our predicted and measured or observed data. And this residual data will contain all the information about all the densities that are not yet, the density distribution that are not yet represented into our model. And we'll actually invert that to try to retrieve the 3D distribution of anomalous densities that are not represented into that geology model. So let's go ahead and compute the response of this model. So at the color table here in the Geoscience Analyst Pro, you can add a column to that table, and that new column will be named density. Yep. Now we've got the density column here, and I'll be able to actually give a density value for each of these geological domains. So these values are residual densities because we're using terrain corrected gravity data, and the terrain correction was done at 2.67 grams per cc. So these values are actually densities minus the correction density here. So I'll just enter these. A denser density here for the ore body. Millrock member at 0.015. Blue Lagoon, a member at 0.056. And the club member at 0.0163. So once I've initialized that density column, I will actually display the density property that's on my block mesh here. And now we're looking at the homogeneous densities attributed to the geological domains. And that's what we'll use to compute the response of our model. For this, I'll go under the geophysics menu and select Compute Forward Model. On this window, I'll choose the type, which is gravity. Observation points is airborne gravity, still shown here at top, and the data here at GZ. Topography, I will select the topography surface already present in the workspace. 3D model is the VOI25, so it's the block mesh shown here in the background. And I'll select the density property we just created. And the output name here will be named Flin Flon GZ response. And I click on apply. So now Geoscience analyst is computing the geophysical response of the model, so the gravity response from this density model, and we have it here. Now, if I look at the airborne gravity point set here, I've got two new properties on it. I've got the response of the model here. So that's our observed gravity signal, the computed response, and the residual, which is the calculated response minus the observed data. So this residual represents all the density, the gravity anomalies related to density distributions that are not yet represented in our model. And the next step will consist of through an unconstrained inversion to actually invert that residual onto the same block model mesh. To do so, I will go under Geophysics, Compute Unconstrained Inversion, Gravity. I will select the same points. And for our input data, now I will select the residual. I will set the uncertainty level. So the error on my data is 0.1 milligauss. Topography here, I'll select my topography surface. The block model here, I do not have to select any property because the unconstrained inversion only needs the mesh, so the block model here to run the inversion. And I will name the output name of my inversion. So the inverted density will be called anomalous density. I will not run this inversion during this lecture, just to save us time, because it will take about 3 or 5 minutes, depending on your hardware. So I've already run this inversion, and the resulting model is already on our block model. So I'll hide the data, and this is the result of the unconstrained inversion of our residual. And now, using a script, I will add this anomalous density back to our geology model, to our initial density model. And I will bring a script. So on the object, that's our block mesh. I don't do any masking. And I will name our output property Flin Flon inverted density, and the script will be density plus anomalous density, and I click on apply. And now I can see on my block mesh, I've got a new property here called flame's-on inverted density. So this is a 3D block model. And you can see the combination of the homogeneous densities and anomalous densities gave us further insight on the 3D distribution of the data within the domains. This can be used to see the model as well, to evaluate if the dips that are represented between different geological domains are optimal or not, and also if geological domains might have been omitted and might need to be represented in the model. So it can be quite an interesting tool as a first foray into constraint modeling on the geological model. And this is concluding our scripting lecture for today, and I'll hand it back down to Carla.
All right, thank you, Thomas. That was great, and thank you to everyone who joined us today. Does anyone have any questions? Feel free to type them into the Q&A or raise your hand, or yep, just yell them over the mountains if you have any questions. If you do have any questions in the future, don't hesitate to email us at support@mayergeoscience.com. And we'll just wait a little bit more. We've got one question, Thomas. Could you comment on where some geological changes could be applied to the last model?
Geological changes on the last model. I could comment on where they might not be applied. If we look at the current section here, we can see that here, a view from the south, we look at our original density model. So we can see we have quite a contrast here in density between this domain here and this one here. And our inversion kind of like kept quite well the density contrast between these two units. So that would actually help me in identifying that that dip is probably quite close to what it should be. Here, actually, if I actually move this section further to the west, here you can see that there is something in the center, and so we're in the same domain here, which is the Blue Lagoon member. And if we're looking at the inverted density, we can see that in that Blue Lagoon member, we've got quite a zonation with the distribution of the density. We've got a denser volume here and a lower density volume here. So that will bring a question about, is that Blue Lagoon fairly homogeneous, or is another density domain needs to be created there?
Great. Let us know if you have any follow-up questions on that. We have another question. Oh, he said, great, those were good examples. So we're good there.
Yeah.
And then we've got another question. Could you do this on a grid to normalize data from -1 to 1?
It's totally doable. Just using the previous script before, you just need to my script for the radiometrics here was optimized for normalization between 0 and 1, but you could change these bands from -1 to 1 if you wanted to.
Nice. And then we've got another comment that it's a pretty cool scripting functionality, but it looks a little hard to edit it right in that input field. That if there's any plans to expand it to maybe hook it up to a coding editor of some sort. I don't think there's any immediate plans for this. I don't know, Thomas, if
I'm not aware of expanding it to a coding editor of some sort. But one thing is sure, this is the first implementation of scripting in Geoscience ANALYST, and for sure we'll be updating and make this tool greater as we get feedback and as people are using it. So it will for sure get better with time. And we're pretty happy just to have it implemented in the first place.
Nice. And we've got one more. Would the scripting steps be similar in GoCAD?
It would be slightly different with the scripting in GoCAD, because the scripting editor doesn't in GoCAD doesn't work exactly the same way. So
okay. Is there anything else? Again, if something else does come up later, don't hesitate to send us an email at support@geoscience.com. I'm still watching out to see if there's any more questions. But in the meantime, I'll let you know that next month's lecture is all about Python, where Dominic is going to be showing how to use the Python in Geoscience Analyst Pro. So if there's no more questions, then thank you everyone for coming, and we'll see you soon.
thanks everyone. Bye.